The Alternative Natural Philosophy Association presents Clive Kilmister, Ted Bastin and David McGoveran in conversation during the month of December 1992. The recording took place in Cambridge.
I think taking a historical perspective is fairly important with ordering operator calculus, because this relates a lot to what I was saying the other day about the importance of communication in my view. And it's rather difficult to cast the whole thing in a this sort of linear sequence of speech, because it didn't really happen that way. It was multiple approaches to what I hope is a common end. Generally speaking, my interest has always been in finding a way to express formally my view that the world is not divided up into physics and biology and linguistics and genetics and what have you, not to mention experience, and in particular the experience of the common man that doesn't have formal training is suitably uncontaminated by formal training. But to really find a way to present it all uniformly, and to some degree I think that was the goal of natural philosophy once upon a time. It, in a more restricted way, is the goal of people going after unified field theories or theories of everything, as they're sometimes now seem to be called. But I think it's a bit broader in conceptual scope, and in particular, I have found it very distressing that I can use differential calculus when dealing with hydrodynamics. I go over to computing, and this is computing science, and this is not terribly useful to me, except that I can implement these things, simulate these things in computing. So I have to change my mathematics to deal with that particular domain. If I work in linguistics, neither are terribly useful to me, and so I end up changing formalisms as I pop from one domain of knowledge and experience to another. And I find that something's terribly wrong about that. It says because we don't, although there is some notion of change of domain, it's not a new world that I can talk about linguistics and genetics in the same breath, and physics, and
you can or you can't.
You can engage in these discussions and compare them and contrast them when talking to someone. Not very well, perhaps, but you can do it, and that is, you can point to the experiential side of it, and rather straightforwardly. It's the formalism where one bogs down and gets into great trouble. So, to some extent, there is a broader perspective about this outside of the sciences per se, and that's cross-culturally, or say between two cultures, anthropologically speaking, or sociologically, subcultures within say in the States. There are lots of subcultures, and they have different modes of speaking and understanding the world, and they don't necessarily communicate very well. That again is a formalism problem. That is, we don't share common terminology, and it's very difficult to find out what terminology is seen differently, to sort that all out. There's not a good methodology for doing it. Now, I spent quite a bit of time through the 60s and 70s in delving into the various sciences and numerous studies looking for some kind of a solution to all this. It had been my hope that Physics would provide some clues because it's supposed to be one of the more rigorous of the empirical sciences. It had been my hope that the study of linguistics and of learning studies and so on, cognition, communication, would provide some clues, primarily because they're about as close as one gets to trying to formally study the issue of how you move across changes of understanding and meaning from culture to culture. And in mathematics, looking at the foundations of mathematics for clues, looking at logic and studying logic, in the hope of finding the right way that one should be presenting these things formally and carefully and precisely. I was uniformly disappointed, always for different reasons. Logic was terribly distressing because I was taught early on by my early logic professors that the predicate calculus was a wonderful thing. And the deeper I delved into it, the more disenchanted I became with the treatment of paradoxes and the notions of undecidability, notions of completeness, and so on and so forth. And they seemed very rigid, ultimately, as well. Physics, I think we've discussed a little bit some of our disenchantments there, mutual disenchantments with physics. But in general, I can't say that there was any particular discipline that said, this is the way to go. This is the place where, someone's got a key here, even if they don't recognize they have a key. And mostly, I came to some conclusions about, by treating all this as being a part of one world, I started looking for, shall we say, least common denominators across them, things that were in common with all of the approaches and seemed to be things that one couldn't do without for one reason or another. And there were a couple of things, I've forgotten how many now, but just to mention a few, that seemed to be absolutely essential. One, I came to a conclusion that reliance and formalism on infinities or infinitesimals was not a useful practice. And so, sort of by exclusion, this left one looking for something that was a finite formalism. I found that although I didn't consider it to be, I didn't give it this kind of a name at the time, that indistinguishability was of critical importance. That there's always a notion of not being able to specify the differences between two things, two formal objects. In order to make the thing, this formalism extensible, it needed to be constructive. You needed to know how to repair any mistakes you had made. And all of these led to a number of problems that had to be solved because those ingredients already in common practice are seen to represent a branch of mathematics and formalism, or if you wish, in logic, that's so restrictive that you can't really do much with it. There was one other thing that I eventually came to after spending quite a bit of time studying the various approaches in mathematics that were discrete approaches, and in particular the one that I felt most comfortable with ultimately was lattice theory. I eventually came to believe that the missing ingredient in many of these approaches, something that was absolutely essential to all the empirical sciences, and something that was driven by my sort of process view of the world, was ordering. And it seemed that no matter which way you turned, ordering was always put in from outside. It was this separate kind of almost meta-mathematical concept that was, you could put it in or take it out sort of at will. And it was not an intrinsic part of the mechanism and so on from the beginning. So the mathematics did not have a process characteristic to it a priori.
I would like a little bit more about what you mean by ordering
Yes.
in such a wide range of contexts.
Mm-hmm. Well, generally, it is common practice, I think, in all of the empirical sciences to refer to structure.
Mm-hmm.
And generally without giving any account as to how that structure comes into being. Mathematical objects are, through some sort of vague notion of reductionism, are assigned to objects at different levels of structure complexity. In physics, we might talk about atoms, and we'd give a symbol for representing an atom, and then at a different stage of analysis, we would give a symbol to the components of the atoms, and so on. But the relationships between these are pretty vaguely expressed, and generally in words only. So when one makes a transition from one level of analysis to another, well, we do this in the text, and then we go on.
Yeah.
So there's this sort of structural scaling notion is not inherent in the mathematical scheme per se. There's some notion of set containment and things of this sort, of course, but it's extremely loose, and for finite and discrete sets, it gets even looser and less applicable to the needs.
But it's really a level structure you're talking about in our terms.
No. That's a piece of it. Early on, I thought that there were two kinds of orderings. That there was this kind of structural and hierarchical, if you wished, ordering type of principle, and then there was something completely different that was like the linear ordering that is a time sequence or some such. And I was dissatisfied with that the more I played with it, because it, in some of the sciences, in particular some areas of knowledge study, that's highly artificial. There's no reason for someone to pick a particular time sequence. And this is true, for instance, with psychological time. And notions of what constitutes an object or an image in perception.
Of course.
There's
So may I just interrupt?
Yeah.
You could say that Clive and I were originally concerned, I mean, putting it in your language, to reconcile these two types of ordering by observing that in a certain particular case you couldn't define a sequence, you couldn't linking them by the case where you couldn't define an order.
Okay, all right. That I have to address that in a minute, I think, because this leads to this business of totally unordered situations or unorderable situations. Yeah. I chose a little bit different approach in which, rather than assuming that one orders things, I assumed that they only came into, if you will, formal existence through ordering.
Mm-hmm.
That is the only sense in which there was any meaning to it. Early on, I tried to express all of this in terms of ordering relations. It could be total orderings, partial orderings, what have you. And this means that if you take the ordering relation as, or a set of ordering relations, types of ordering relations, as being primitive, then you have to start understanding things like set containment and so on in these terms as well. And of course, lattice theory contributes a great deal to this. But that still makes it kind of a separate concept. there's the thing being ordered and the ordering relation between those things. So I wasn't very happy with that. In trying to deal with circumstances where there were multiple orderings, relationships between collections of objects, formal objects. Let's say I had A, B, and C. There might be a particular relationship, total ordering between A, B, and C, so that B is greater than A and C is greater than B, and therefore C is greater than A, so on. But there might also, in addition to that, be a separate ordering such that C is less than, in that ordering, C is less than A. Now, trying to express that with the usual ordering relation kind of formalism is painfully difficult. It falls apart very rapidly. And so one of my early attempts at this was to set up sort of a matrix of ordering relationships that said, given this, if you will, this sort of vector of objects, here's a matrix of ordering relations that apply to that vector of objects will show what each of those objects are related to, given the particular relationship that's operative in this system. So it generates a sort of a new vector of objects and tells you what it's connected to, if you will.
Yeah. Could I interrupt? I don't want to stop the flow, David, but I just wonder in that context whether you're, in terms of ordering, you're talking entirely of ordering relation between two entities.
No.
There's betweenness.
Yeah, that's exactly the problem with that particular way of trying to express this.
So in your example just now, you were really talking about the first thing you described, B was between A and C.
Yes.
And you might have had another situation where B was not between A and C.
Right.
Yeah.
Yes, that's right. So some of these, for some of the relations, they might have been, shall we say, isolated, and in others they might have been related to multiple other objects and so on and so forth.
But ordering here for you means ordering between more than two elements sometimes. Can be.
Right. Yes. Yes.
Right.
Absolutely.
I mean, this fits in very well with what Ted and I were doing in the concept of order
Yes.
papers.
Yes.
Yeah.
Which was a pleasant surprise to discover later on. And actually, just to put this in kind of give it some time sequence, the matrix representation of this ordering, sort of the precursor to the ordering operator concept, that came about in about the 74 time frame. And I, by working with it, I very quickly came on this problem of how do I represent a situation in which what I really want to say is that object A is in fact related to multiple other objects. And now I don't have a clean way of expressing the new array of connected elements. Well, that eventually in the roughly the 78, 79 time frame, which was about the time I started communicating with initially with Ted. I met Pierre in 76, 77. Later, actually, I think it was in 77, and he suggested that I send a paper I had written on multidisciplinary modeling methodologies, was the title. That relates to this business of coming up with a methodology by which you can explore how to relate concepts from one discipline to another, or between two cultures, say. Any place where there are apparently two different ways of expressing concepts and relationships. And so I sent that paper off to Ted. About the same time frame, I started generalizing this sort of matrix representation and came to what I now call an ordering operator. In 81, I wrote a paper called Getting into Paradox Towards a Finite Discrete Differential Topology. And really, in some sense, although the first part of that title was motivational, and because it was treating paradox as being a crucial problem in formalisms, it was really the second part of that title, which was the sort of the more descriptive aspect of the paper, and that was the first version of this paper that eventually was published. Gosh, I guess not until June of '89, called Foundations of Discrete Physics. The other thing that's interesting is that first version didn't refer to physics.
I was going to say, there is a certain sense in which I regret the change from the first to the later version.
Yes,
That
yes.
discrete topology stuff was wonderful.
Yeah. Well, it's all still there. It's just
But it's harder to find it.
A wrapper has been put around
Yes,
it.
it has, yeah, plain
unfortunately.
wrapper.
So the but even in that even in the although the foundations paper was written in the 84-85 time frame and eventually distributed in late 85 and 86, you see it took a full 3 years to get it published even as a Slack pub. So it's the material has been around for quite a while, and in the process of all that, I've changed, learned, I think is the way to put it, better ways of expressing the notion of an ordering operator and so on, so that I've tweaked the way of representing these things and dealing with them a bit. In those earlier papers from the 80s, although I think the essential concepts have not changed, I didn't focus on some aspects that I now wish I had, because they turn out to be the ones that people seem to have most difficulty with. On the other hand, that may be a result that I didn't treat them in the papers, so it's that there's some explanation that's working. The basic notion of an ordering operator and its importance hinges around this process view. And in fact, that was integral to the modeling methodology business.
Sorry, hinges around which process?
It hinges on the process view, a process-oriented
a process view. Yes, yes, yes.
Right. If as soon as I try to tear these things apart, I get into a dualism, and it raises all kinds of philosophical problems that including the paradoxes. You're led to a number of rather nasty conceptual paradoxes in short order. Those paradoxes are normally represented formally in continuum mathematics and shall we say, logical systems where the number of elements can be increased ad infinitum. Even in recursion theory, which is taken today as the basis for computer science, one assumes, and the notion of Turing machine, one assumes that you can just go grab another piece of tape and tack it on, keep extending the size of the things. And so you start looking for ways to get out of the paradox by appealing to these infinite extensions. And in some cases, the arguments sort of work. They don't work real well if you start looking at them closely, but they sort of work. At least I found them unsatisfactory. So the business of tying up ordering with each object, each formal object, has always been essential. And to give you a rough idea of what I mean by that, or what you can do with it, let's see, I think I better take this with me. Where's our sheets? The simple case of an ordering operator is this notion that I would have, oops, what did I do there? I meant to go across that way, create an A. I can't write A's today. It's rather as if each little element has an arrow attached to it that represents its connectivity. And in fact, it has sort of the open end of an arrow coming into it, one or more of them. Okay? So that these are like keys and locks in a sense. And this says that in the context of this element being generated, an element is always generated from an ordering operator. The total of all elements generated by an ordering operator, let's take a simple case of a complete total ordering, this kind of thing. The totality, so right here I'd have, oops, I should put another arrow in there. Getting a few out of hand here. There we go. So it's B, C. As you can see, I frequently leave out the little circles because it's inconvenient to write them. I end up just drawing the arrows. But let's say that we have essentially a chain that's A, B, C, D, E, and so on. It has an initial and it has a termination, right? In this particular case, and so we could say that's ordering operator, and we'll give it a star or some such to designate that particular ordering operator. This is the totality of what that thing can generate, and it has a particular sequence in which it's generated. In this case, it is a total ordering operator, so it doesn't. There's only one place to start that you can start, and there's only one place you can end up. But that's not always a given. I can have more complex situations. Yeah. For instance, and now this time I'm going to leave the arrows will be implied in the direction in which I draw the lines. I might have this kind of thing.
Yeah.
All right. I can also have this kind of thing. Right. I could have this kind of thing. Right. Now, clearly the end result is a directed graph. Right?
Yeah.
But it need not be an acyclic directed graph. It need not be a directed graph that can lie in the plane. It could not. It's possible that you can't even draw the thing in the plane. So, for instance, we might have. Let's see. I think this will do.
You've got to have a Wheatstone
like that,
bridge
right?
in it.
Yes.
That's right.
Right.
Yeah.
So you can and well, we need to do that, and that'll tie it down. That makes it perhaps more difficult. Maybe draw one underneath to make it even nastier. So you can't flatten these things out necessarily. Well. So it's very general in terms of the number of starting points, the initial generation of the ordering operator, and its conclusion. It is this entirety with the directions noted, and each of the elements understood as in this particular way, that defines the ordering operator. This is just a compact notation for this. Right? When you talk about the thing generating, that's a decomposition into states.
There are no elements other than what is produced by the ordering operator.
Yes.
Not even the starting element.
It is. That's right.
Right.
It is
Okay.
generated.
Yes.
Yes.
Holy.
It's as if one says, "All right, do something,"
Yeah.
and I can't tell that you've ever done anything before.
Don't
do
just
something.
sit there, do something.
Yes. Right.
All right.
All right. So you can see that since this is a total ordering in this particular case, it's rather easy to see that this is a recursive generation, and you can think of this as decomposing into a series of subgraphs being generated, increasing in complexity. So that first we generate A, then we generate the subgraph A to B, and then the subgraph A to B to C, and so on. So it just increase in size.
And is that a special case in being recursive?
No.
They're all recursive.
They all end up being recursive in considerable more complexity, but they do. And this is an important part of the trick.
Yeah.
In particular, and this is to give you a rough idea. This is where you start seeing some of the difficulty with this particular directed graph. We've generated two elements at once in one step, as it were. Right. Well, so this is a partial ordering in the usual lattice theoretic sense. But what's interesting is that from the context of the ordering operator, these two elements are indistinguishable. We can't tell whether we're here or here. There's absolutely no. We can know that the cardinality is 2, but that's all we can know. Right? That can be part of the definition of the ordering operator. So, and I don't want to go off into a long discussion of this because this gets very complicated in short order. And in fact, I've looked at what I really thought would be necessary for this, and then roughly just going through the, shall we say, elementary ordering operator mathematics is probably minimally a semester-long course, and a graduate level course definitely, because it would require that degree of concentration. We obviously don't have that here, that much time. But a couple of key points then is that when we go beyond this kind of simple partial ordering and we start having this kind of situation, the nature of the recursion depends very, very much on this business of indistinguishability. It's absolutely essential. You cannot express the recursive characteristic. It's not simple recursion, by the way. I should, it's generalized recursion.
Yeah.
But and so you can't really express it without understanding this notion of indistinguishability. Any element, even though I've labeled them here, does not have an intrinsic label. Say, its position is understood only by its connectivity. Right? So a curious thing happens. Up here, for example, without being in the context of the ordering operator, I really can't distinguish that element from that element. They have the same connectivity, right, with all the other elements.
Well, I mean, yeah, but without the ordering operator, they're not there at all, are they? This is the ontological worry you're gradually building up for me.
Yes, that's right. Yes, and bear with me. It's
okay.
Of course, it's not there except that the ordering operators are there. They are joint presentations, if you will. But what I was saying is that I can be either sort of inside the ordering operator or looking at the ordering operator from outside. All right, I can take these two perspectives on it. That is, that I have knowledge of the operation of this thing, okay, or I don't have knowledge of it. The point is that the recursion, the algorithm that defines this general recursion, in this case or in this case or any of these other cases, can be so complex that I cannot represent it explicitly. Okay? So I may not be able to understand how this thing does what it does, okay? Just in terms of its complexity. Okay? It's not that it is not generally recursive, a general recursive function. It's just that it is too complex for me to represent and explain.
Too complex for David McGoveran to represent and explain?
Perhaps for anybody. Okay?
Well, therefore,
Perhaps.
for anybody.
Yeah. Yeah, but no, I mean, this is, yes, but this is a, I mean, is this an impossibility of a Gödelian kind?
No.
Oh, anyone
Remember,
in the finite universe?
Right,
okay.
yes, exactly.
Yeah.
Okay. This gets us to a better, I'm going to try to lead us down the primrose path to a better understanding of indistinguishability. Indistinguishability, for my purposes, is defined as a lack of distinguishability. Okay? That is, it's what one is forced into because you can't distinguish two elements. If I have a finite discrete space, I can show that there are some algorithms that cannot be represented within that space. I don't have enough symbols to represent everything. Okay? So it's not that the algorithm cannot exist per se, it's just that it can't be represented in a certain space of which I am knowledgeable, which I have awareness, or which has been generated so far, perhaps. Okay. That turns out to be important not only to understanding the indistinguishability of these elements from outside the operator, but also internally, when I generate something like this, what I mean by these elements that are being generated, by the objects that are being generated. Because part of the whole notion is some kind of a funny kind of notion of embedding, that this object, what is treated by an object by the ordering operator, could in fact have a tremendous complexity to it. It could in fact be another graph. But the rule is that its complexity must be such that in the context of the space of this ordering operator, the number of elements that it generates, its size, if you will, and its complexity, that this could not be represented. The algorithm for this could not be represented explicitly. So it's all collapsed into a single element. Sort of all that information is thrown away from the perspective of the algorithm that defines this ordering operator. That turns out to be absolutely essential to building up larger and more complex objects and to this notion of attribute, a combinatoric attribute as I've referred to it. Let me take a simple case. Suppose that I had an ordering operator that looked like this. And again, the arrows are implied going from left to right in this case. And I will label these arbitrarily in this way. Because of common pattern. There's a pattern here, a pattern here, a pattern here, and likewise here, here, and here. Different patterns, right? So I give these to represent the fact that there's an equivalence relationship that can be defined across these. I give them the symbol 1, and I give these the symbol 0 arbitrarily. Fine. So now I can say that this thing is repeating. It says 0, 1, 0, 1, 0, 1, 0, 1. Okay, in a rather straightforward way of representing that. This is an attribute. It is a subgraph that has a certain relationship. It expects that these two elements are coming from a single element, a previous element, and going to a single element afterwards. This one has a certain characteristic, namely it's coming from 2 and going to 2. Right? So each of them is a well-defined pattern in that sense. I could take something that's even larger. So let's do the same thing over again and define a different combinatorial attribute. Take those 3 at a time, right? Okay. They have the same connectivity.
Yeah.
They are the same attribute. Each is a different instance of that attribute, but they're the same attribute. Okay. Looking at it this way, I can start talking about distance. Because here I can say the ordering operator has gone through generation sequences 1, 2, 3, 4. I can enumerate the recursions that generates this digraph. And I can say, well, but it's 2 steps of the ordering operator to get from 0 to 0. So if I start looking for occurrences of zeros, of the 0 attribute, as I've labeled it here, I can say, well, they're 2 apart, okay, 2 steps apart. And it happens to be uniform. It need not be uniform, of course. There could be lots of other things that go on in between each of these stages and in a non-uniform fashion. Okay. Now, for just a moment, I want to point the way to the next bit of complexity. Not get into it very much, but it's essential to talking about this business of dimensionality and coordinate spaces. Suppose I have multiple ordering operators. Right? How can they possibly combine and interact? Well, remember indistinguishability. So if I have yet a third ordering operator, and I'll draw it a little bit trickier, do something a little bit more complex, right? Okay. At this point, this ordering operator generates the same attribute as this one. If my space is such that it holds, it's big enough to hold this one and this one, okay, I can't tell whether I'm here or here in this attribute. There is no way for me to distinguish which ordering operator from the outside, which of these is doing what. Okay? So they cross each other, and they can become confused, can become intertwined. They can cross over. Okay? So that if I start here, I may suddenly switch over and generate on this ordering operator. And if I start here, I may switch over and generate here. And that complicates the statistics of any given situation. In fact, it's at this point it remains an open problem to understand exactly what those statistics are for a graph of degree n and certain complexity, a number of arcs, etc. In fact, it's also an open problem as to the number for a given directed graph to define with a certain number of starting elements and a certain number of ending elements to define the number of ordering operators that can be defined upon that graph. Okay. There may be more than one that is possible, but then that defines that is to say, ways in which you can draw the arrows, okay, so that you don't end up with isolated subgraphs. Okay. It's a huge number.
It's very much into discussing how many ordering operators can dance on a pin.
Well, it may be.
If I think of them as angels, I get a better.
Does it? Could I just go back, David, in case you're going to tear that off because you'll need some more space,
right.
And take the earlier two examples.
Right here?
And
or
no,
here
those two, yes.
Yes.
And you remarked that you could define a distance because yeah, okay, that's all right. But now, the actual graph there is exactly reproduced down below, but as I would put it, interpreted in a different way. You've drawn different circles around it.
We're examining a different attribute.
The same ordering operator, but a different attribute, I
Yes,
see.
an attribute of that operator.
Oh, very
Right,
good.
right.
And so the distance is a property of the attribute.
Yes.
As well as the ordering operator.
Yes.
Yes.
Absolutely.
I see.
Yes.
Oh, that's
Indeed.
That's this attribute distance that comes
Yes.
up. Right.
Right.
Could you say that again, Clive? So what
Yes,
does what?
you see, he was saying he said you could say there's a distance 2 between the noughts on that example, which is now in the middle one, the one that's got 0, 1, 0, 1, 0, 1 written on it. He's saying there's a distance 2 between the noughts because you've got to operate twice. Or say that, there are 2 circles drawn between the noughts. The very same graph down below, he's drawn the circles in a different way so that each one's got 3 bits in it. And so the same way of talking seemed to me to show that the nodes would have unit separation instead of 2.
Yes, exactly.
And David says, yes, that is right, because the distance defined is an attribute distance. That means that the different ways of drawing circles are pointing to different attributes of the graph. And the distance depends on the attribute that you're talking about, not merely on the ordering operator.
Right. It is roughly speaking, what pattern are you looking for?
What pattern? Yeah.
Right?
Yeah.
So, and I had mentioned the other day that this is a general notion of pattern. It could be the case that I say, well, it could be these 3 and out of them connecting in any way whatsoever. Okay, so there could be an open question mark on part of the pattern, right? Or up here I could say, all right, I've represented the attributes. I can do some abstraction and say this 0, 1, 0, 1, 0, 1 is a representation of this ordering operator, and now I want to look for patterns of the type 0 anything, 0 followed by anything immediately. Okay, so whether it's a 1 or a 0 doesn't matter to me. Okay, and now I look for that pattern as my attribute definition. Okay. It's as long as I can define, and so again, it has to be recursively definable. So it has to be an effective procedure by which I can define what I'm looking for, right? So that I can recognize it. A decision procedure, if you will. Let me make a couple of statements. First of all, about the combinatorial hierarchy and the relationship I see between the combinatorial hierarchy and ordering operator calculus. All of this business, I think, has to come first. That is, my perspective is that you have to have some notion of how you're going to run mathematics before you start talking about how you're going to do counting and how you're going to do identification of objects and all this sort of thing. That this is not given in mathematics. We have a tradition in mathematics, certainly, and that for the most part looks back to Frege. But there are some good reasons why it may not be adequate to our needs. And so these foundations need to be laid somewhere. and understood carefully. And if once you've done that, then you can look to a particular structure, such as the combinatorial hierarchy, and say that it has some kind of significance. To talk about it, about even counting, unless you have something to count, you know what it is to identify a something, so that it can be counted. I don't understand that at all.
Yes. Unfortunately, there are other people who won't be able to understand abstract discussions of mathematics. I mean, it seems to me to be a psychological difference. It's indeed one of these cultural things that you're so keen on.
Right.
So I mean, you must have noticed the glazed expression in people's eyes when you go on. I mean, I'm beginning to see how, but I have to interpret it as I go along.
Mm-hmm.
Not
Sure.
in physical terms, but in some terms I have to interpret it.
Yeah. Well, I think that's part of the problem with abstract formalism of any kind, is that one doesn't understand abstract formalism until you have interpreted it
That's
in many
right.
times and in many ways,
Yeah.
actually. A single interpretation of abstract formalism is not an understanding. It means that you have only said, well, I have a glimmer of what this is about, and I can use it in one particular way. But that denies the whole point of having it be abstract in the first place. You've made it concrete in a sense. But it is difficult, and it's I don't think that it's, even though we work very hard in our society to teach set concepts and those foundations of mathematics. I mean, our language has become imbued with the terminology, and yet it takes quite a long time for people to understand these things. And I'm not sure that they do anyway. It's when you start really teaching foundations of mathematics and exploring foundations of mathematics and set theory, there are no end of surprised looks on students' faces. So, in any case, so from my perspective, combinatorial hierarchy comes after you've set this sort of foundation work and the way in, you've told me how you're going to be talking to me, and then you're going to talk to me. And so at least I have some hope of being forewarned that you're talking in a different way than I might be hearing. And whether it's through the ordering operator calculus or through generation functions or what have you, the combinatorial hierarchy has to be represented in some way. And the question then is whether or not that way of representing it is consistent enough for the purpose at hand, the ways in which you wish to use the combinatorial hierarchy, and whether it is complete enough. So, or whether, if it's not complete enough, can it be extended sufficiently? Is it a sufficiently open system? All right. Well, I can think of one of the bits that's in the foundations paper is to show that the ordering operator calculus is rich enough so that I can think of any generation of the combinatorial hierarchy as though it were an ordering operator. Right.
As though the totality of an ordering operator.
It can, yes, it can be. I could also think of it as a set of ordering operators, a collection of ordering operators that are interacting in a certain way.
Yes.
It depends on how I choose to define distinguishability in the desired interpretation of the combinatorial hierarchy.
Yes.
Do I want all the elements at a given level to be indistinguishable, right? In that case, certainly I could have a three-step ordering operator that would just give it in its entirety. If I want it to have further structure, then probably not. Probably this will be a set of nested ordering operators where in some sense, I'll have the generation from level to level, right? And underneath this, in some way, the generation of the discriminantly closed subsets, right? That tell me how to translate.
I've been thinking more of the two progressions in the hierarchy, which I'm thinking one of these is more appropriately thought of as an ordering operator than the other.
The way I've thought about it is that they are, the convenient way for me to think about it is that there are minimally two ordering operators. That's not strictly speaking true. I think it's possible to collapse the two sequences into a single ordering operator representation, but you lose a lot of important information in doing that. That is, it's not immediately accessible at the global level, right?
But,
That's this whole point of complexity again.
yes, but one's more ordered than the other.
More complex in my terms, yeah. I think you're using that the same way as I use complexity.
I see, okay.
Right. Degree of ordering, number of elements generated, how many indistinguishables there are, the degree of the ordering, if you will, at any given stage, whether it's a partial ordering, a total ordering. Total orderings are somewhat simpler than partial orderings, and there are myriad kinds of partial orderings, whether it's cyclic or acyclic. Those kinds of things change the complexity of the situation. Yeah.
Some animals are more equal than others.
yes, that's right. Well, again, equivalence takes on a different character in the ordering operator calculus. It is equivalence under what ordering operator, or what set of ordering operators.
Right.
You can't simply say they are equivalent. This is the distinguishability problem. Right. Can I, within the context, define an effective procedure for distinguishing these two elements or not? And having done that, now I can say what I mean by equivalence. I've defined an equivalence class. It's not appropriate to say that A equals B and leave that standing. It's A equals B in what context? In what context of generating these elements? Right.
Well, I certainly find that very natural.
Well, I do too, but it's usually not a part of mathematics.
No, I mean, I don't want to dissociate myself from what Ted's just said, but on the other hand, I am gradually developing an acute ontological problem as you go along, because it seems to me the whole world has been dissolved away, and I have no firm objects except in the context of an ordering operator.
Good.
So I never can have, I can never ask whether this one's the same as that one, or
Quite right.
Or
Yes.
indeed, when I've got that one, I'm not sure whether I've got this at all.
Mm-hmm.
Okay, I see.
Yes.
Well, I'm learning
Yes.
then. Yes.
Good.
Oh, I didn't mean to say that the whole thing was clear, was natural to
No,
me.
no,
I only
but
meant
that-
that
well, yeah.
this use of equality was natural.
This is how I was agreeing with you up to a point, but
Yes.
expressing my discomfort.
Yeah, this is wonderful. I actually feel like I'm communicating because you're uncomfortable.
Yeah.
Because what?
Because you're uncomfortable. Unless he gets uncomfortable about something.
Uncomfortable, you did say.
Yes, uncomfortable. Right. There's
In a
something-
well-known phrase, if it isn't hurting, it isn't working.
Yes, that's right.